All right, any questions about the homework I posted? Did you all see it? The solution? Anything? You got a question? Shoot.
So 1 minus t, or x of t is 1 minus t.
X of t, hold it. 1 minus t.
And it has p1, which means it's correct.
Pardon me?
Oh, p of 1, which means it's like a correct.
Pulse function. Pulse function of 1, t,
And t minus
t minus what?
1 half.
1 half. Is that it?
You have to find the full year.
All right, now, there's 3 or 4 ways to do this. It's totally up to you. I'm going to start by doing this. If I look at this thing right away, I can break this apart as simply P1 of t minus 1 half minus t times P1 of t minus 1 half. Do you agree with me? Everybody? Now, if I do that, the next thing I can do is say, well, the p of t minus 1 half is common in both terms. Why don't I find the transform of that? So if I take this and I'll put it over here, and I'm going to tell you, remember, you don't get tables on this test, so you have to know the basic transform pairings for both Laplace and Fourier, the basics, like pulse, impulse, u of t, e to the minus at times u of t. And then you have to know the properties, like modulation, when t times x of t, the general properties. But I don't ask anything way out in left field. Everything is based on the homework where you've seen that property utilized over and over again. And you've seen the transform pairs over and over again. So for the pulse function, we know the pulse function of t is the same thing as the rect function of t over tau. Do you all agree with me? This is tau. I'm going to leave it as tau, and I'll put it in the 1 in a second. Do you all agree with that? Now, if we take that, we know, and you must know this, the transform of that is tau times the sinc of omega tau over 2. Do we all agree? That's a given, right? I'm going to call that x of t. The reason I'm doing that is because I want you to think in terms of properties next. Now, I know if I know x of t goes to this, which is my x of omega, then it's also true that x of t minus any coefficient, any delay, transforms over as what, class? What does that time delay do in the frequency domain? It's going to add a phase term, e to the minus j omega times the delay, right? Times tau times the sinc of omega tau over 2. Do you all agree with that? Now, I should say this would be the p of tau of t minus 1 half. We go to that, and then here you would actually go ahead and put tau equals 1 and alpha equals 1 half. And I'll do that next. It's almost too much information on here, but minus j omega divided by 2 times tau, which is 1, times the sinc, right, of simply omega over 2 is the actual transform of that. Do you agree? That's the transform of this one. P tau of t minus a half, right? So we've got this transform. Now the next thing is, if this right here is my new, I'm going to call this x1 of t, I'm saying the p of tau of t minus a half, or p1 of t minus a half, I'm calling that x1 of t, just so you think in terms of the property. Follow me, class? So what happens if I take I hope you can see this. What happens if I can take t times x1 of t? What does that, I know that, and let me be clear about this, this is right here, this is my x1 of omega, right class? People in the far back see this? Just tell me if I need to write bigger. All right, that's my x1 of omega. What happens when I have t times x1 of omega? The property says t times anything in time means what? I have j times the derivative with respect to omega of x1 of omega. Isn't that right? Class?
Yes.
Please, just tell me, right? Agreed? So now the next logical step is take the derivative of x1 of omega, right? Agreed? You want to do that in the middle board? How would you do that? How about if I say that x1 of omega, I'll define it in terms of its basic elements. So you'll see it. This is going to be e to the minus j omega alpha, right? Times what? The sinc function. Well, the sinc function is what? It's the sine of omega over 2 divided by omega over 2. So just put a 2 up here. Does everybody agree with that? Bless you. Y'all agree? Y'all see what I'm doing here? I mean, do you guys see, right? Or not? You don't? You do? I got to make sure. All right, now take a derivative of that. What happens? When I take a derivative of this, what do I get? Derivative, I can take the 2 out in front. With respect to omega of e to the minus j omega alpha times sine of omega over 2 divided by omega, right? You've got 3 functions of omega, don't you? 3 things that vary with omega. You have, what, the sine, you have a 1 over omega, and you have an exponential, e to the minus j omega over 2, correct? Right? Well, how do you do something like that? You can just take the derivative of the first, right, times the remainder, plus the first times the derivative of the second, times the third, right, plus the first and second times derivative of the third. Do you agree with that? So I'll do it that way. Let's make it a little long and boring, but that's what I'm going to do. So this becomes 2 times quantity. Derivative of the first is going to be what? Minus j omega, right? Or I'm sorry.
J alpha.
J alpha, pardon me. You're right. Minus j alpha, right, times e to the minus j omega times alpha. I think I'm gonna put the, alpha was, this comes out to omega over 2, correct, class? Right here, that's omega over 2, isn't it? So I'm getting rid of the alpha, and I'm just gonna put minus j over 2 just make my life a little simpler, all right? So it's that times the remainder, so it's times the sine of omega over 2 divided by omega, plus the first, which is e to the minus j omega over 2, times the derivative of the second. Derivative of sine of omega over 2 is what? 1/2, right, times cosine of omega over 2, correct, class? I still have to divide this by omega, right? Then I have plus the first and second, e to the minus j omega over 2, times the sine of omega over 2. Now the derivative of 1 over omega, or omega to the minus 1, is a minus sign, right? Omega squared. Do you agree with that? So now this is going to have actually a minus sign divided by omega squared. And that is what? That's the derivative of this, which is the derivative of this right here, x of 1, and I have to multiply this whole thing by j, don't I? So when I multiply the whole thing by j, now I have, in fact, the transform of, this is the transform of t times p of 1 of t minus 1/2. Do we agree with that, class? Y'all see it? Now, I can tell you, just looking at this, we can factor out a lot of stuff. First, the first thing we can get e to the minus j, we should get 2 here. We can get e to the minus j omega over 2 out front, right? Then you can see, you can pull 1 over omega out, right? Correct, class? Now, if you want to carry through the j times j is minus 1 with a minus sign is plus. then we get a J here and a minus J there, correct? And I'm going to say this, you could probably fuss with it and combine the coefficients of sine omega inside there. And you could, you know, make it as nice as you want. But that is, in essence, the answer for this portion of it, right? And we had the answer for what? This right here, too. So that's t minus p1. So actually, we have to put a minus sign here. I'm just going to go ahead and put a minus right there. Follow me? And then you could say, if I take this transform right here and add it, or take that transform and add it to this right here, that's the answer. Do we agree? And if you want to put them in terms of sinc functions, you can, because it's obvious the sinc function is up in a lot of places. If we divide this by 2 right here, we'd have a sinc. Here, if we just factored out an omega, we could get another sinc right there too if we divide by 2. Can't we, class? So you can make it fit the form you'd like, but that is essentially the answer. Do you all agree with that? Who asked that? You asked that, yeah?
Oh, one question. How do you get the 2 over there? Whenever you have the X
Help me out. This 2?
above that?
Here?
Yeah.
Well, the sinc is what? Sine of omega over 2 divided by omega over 2, right?
Mm-hmm.
So I took the 1/2, right, just multiply top and bottom by 2. Okay. That's what it is. That one has an answer, doesn't it? You can get those, I gave you the MATLAB and the Wolfram Alpha links to that, and they'll give you those answers. And actually, in MATLAB, there's one command you should remember. If you want to see the answer in a form that's most understandable, anytime you get an answer, you'll get an A and S equals something. After that, just type pretty. A and S. Do you know that? Do you know this? And it'll give it to you. Does everybody know this thing? Jeff, you must. Remember? If you type pretty and then in brackets A and S or whatever it is, it'll show you it in a form that's very understandable. It'll have, literally, it'll put things above and below, long partitions, long division signs and stuff like this, and it's a lot easier to understand. Just try it, and it makes it easy. Wolfram Alpha, you don't need to do that. I use something for a lot of this stuff, well, for a lot of things in general that you don't probably have access to, but you can download a free copy with some features disabled. It's called MathCAD, and I love it. It's the easiest thing to use. What you see is what you get. Have you ever used MathCAD? By far, for simple stuff, it's much quicker and easier to use than MATLAB. It's not cryptic at all. Has anybody used MathCAD in here? Nobody. Oh boy, you guys would love that. Believe me, if I was sitting where you were, I would learn that because it saves so much time. Did that answer your question? All right. Did you look at the answer they gave?
Oh, but Peter had the answer.
What?
We didn't give an answer on this one.
I think didn't I put it down there? Well, okay, if you type this in MATLAB, or you have Wolfram, everybody know what Wolfram Alpha is? Or not?
Yeah.
Man, go there, they have, I think I put the link there. You just put in, they don't use a pulse function. There's a function they use, they might use rect. Heaviside function is what they use for a lot of things. That's a U of P, basically. Just look this up. And you'll see that they have all the functions that we have access to with slightly different names. U of T, I think, is heaviside. And then the pulse function, I forgot what they call it, but they have it. They might be a rect in it, but they'll have it. Any other questions about the homework? Yes, sir.
Mainly for all of 2,
What's
main
that?
thing is, were we supposed to be using duality to solve
Well, you can use anything you want. Which problem? I need a problem.
just for simplicity's sake, whereas just the triangle function stands
Yeah.
around -1 to 1.
It's anytime you see a triangle or pulse, it's either direct or duality, one of the two. I mean, if it's a triangle or a pulse in time, then you've got the transform pairing, right? Pulse in time, it's sync, right? Rectangle, if it's a triangle in time, it's going to be what? It's going to be a sync squared, right? With some coefficients. So is this in frequency domain?
This is
Yeah.
in frequencies.
All right, we'll do this. We'll do a few of these. And by the way, again, I'm going to underscore this. Duality is the strong, in my way of thinking, the strongest or the thing that makes a Fourier transform so powerful is the ability to use duality for almost anything. So as soon as you know the transform pairing from time to frequency, automatically you know the pairing. If you revolve that thing, take the time domain function, put it in the frequency domain, now you know what caused it in time, which is really nice. Now go ahead and give me the one you're thinking about.
It's a triangle function from -1 to 1.
-1 to 1 in the omega domain?
Yes.
And where does it go to?
Let's just say 1.
Okay, this is a beauty. All right, now that function right there is what? It's a triangle function, right? It has a width of 2, doesn't it, in the omega domain? 2, right? That's just centered at 0, which makes it easiest. I mean, it's really easy, right? Now we'll do duality. I'll do it over here. Maybe I'll do it right. I'll just put it right here. Now, you guys know this. If you have a triangle function with tau, it goes to tau over 2 times the sinc squared of omega tau over 2. And while I'm at it, I'll redo the pulse. This is 4, by the way. I'm sorry. Right, class? And we proved that, didn't we? You remember that? All right, now I've got these two pairings. This is like my x of t going to my x of omega. Correct, class? Right? X of t goes to x of omega. We're going to use duality. So now I take x of omega, I take the form of the function in an omega domain. I bring it over here and I replace omega with t, right? Work with me, guys. I need to know you hear me, and I need some encouragement on your part. So this becomes tau over 2 times the sinc squared. Now it's going to be t tau over 4. Agreed? All right, what about this? There's one thing we got to do here before we do anything with that functional form. Class? 2 pi, right? There's that 2 pi factor. Do not forget that. So this has a 2 pi. Then we take x, instead of t, what do we put in here, class?
Negative.
Minus omega. I'm going to make you say that, and that way you'll retain it. The more often you respond to my questions, probably, the more likely you will not to forget it. Trust me, verbal response helps. Do you all agree with that?
Yes.
Now, when we, all right, this is actually, I'm going to go ahead and put the triangle in here, because now we know it's a triangle function with tau n of minus omega. I have one comment before I go ahead and do any scaling. Can that be a plus omega, class?
Yeah.
Why? You're right. Even function, right? Because it's an even function. X of minus omega is x of plus omega, right? In a sense, it's symmetric about the origin, so I'm going to get rid of that negative. Now the next thing I'm going to do is simply because I can see the scale factor, there's 1 in front of it, right? I'm going to get rid of that 2 pi by dividing by 2 pi on the other side, agree? I also make note of the fact that that tau is 2, but first I get rid of the 2 pi. So I just come over here and make this 4 pi. I have 2 pi there. I'm going to divide by 2 pi, I get 4 pi. Can you all see it in the far back? I worry about you. Why are you so far back there?
Normally it's someone right here, so I just.
Well, you can come on down. I mean, you can sit down there, believe me. I don't think anybody's not had a shower, hopefully. Anyway, are we all together on this? All right, now I'm going to replace tau. Tau is what, people? 2. With 2. Don't make that mistake, 2, right? Please. That happens all the time, and I mean, it's like clockwork on a quiz. Every time I do that pulse stuff, they look, oh, it's 1. You know, it's 2. All right, now that means the tau over here becomes 2, and 2 over 4 makes this a half, right? I've been doing this for a while. It drives me nuts to this day. Tau is equal to 2, so this is t over 2, correct? Right? Now, I'm going to ask you, do we have the transform of that back to the time domain? Just look, do we? That's the function we want? Sure, we have this. We have the inverse transform right there, don't we, class? It's over. We've got it. Do you agree with me? Everybody see that? We've got it. I wanted the time domain function that caused that, right? Now we've got it through duality. You asked the question. I hope you see what I'm doing. It's very easy once you understand duality. Very easy. Got one question for you. Now, if this was a filter response, by the way, I'm just going to tell you something. A lot of people would say that's a filter we can build and work with. If that's a filter response, what does it mean? If I take the input, x of t, and I get x of omega, and I multiply that by that filter response, then I get the output, x of omega times h of omega, right? What if my input is a delta function? What is the input impulse response? Well, if you put a delta function into that filter, I would take the transform of the delta function, which is 1. 1 times that is that, right? If we look back in the time domain, then y of t would be this, or y omega. To the y of t that you'd get, you'd have this, right? What's very problematic about that, please? The delta function occurs at t equals 0, right? Tell me about that values of that function for t equals -5 or -6. It's not, it's got a value, right? It's rippling all the way back, which means it's non-causal, understand? Which means you can't build a filter to do what I just suggested. That filter characteristic can never be perfectly good. You can't build that thing exactly, right? You can get close, but you can't build it exactly in continuous time. You know something about causality. I know that because there's a lot of filters, the non-causal filters. Now he's a guy that's been around the university a long time in network services, deal with computer stuff. But when they have data logs, they have strip chart data where they have a log for maybe an entire year of some phenomenon. That means they have a data record. Now you can do a non-causal filter because now you have all the data before time began to when time is forevermore. So in a sense, so you can use a non-causal filter, and we'll talk more about that later. But if it's in real time, in other words, you're at now, and you know what happened in the past, but the future is unpredictable. You don't know when that delta function is going to come in or any other function. You can't build a filter like that. Got it? That's something to be aware of. That's non-causal. Other questions? I mean, we can bang them all out if you want, but they're pretty straightforward once you know duality. Let me just mention one other one. Do you know how I had two of these things shifted in frequency? Right? Let me do one like this, all right? Keep in mind we're going to use this one, right, as the basis. And I'm going to go here. And the reason I'm doing this is because this is particularly important to recognize as electrical and computer engineering students. Really, it's important for any engineers or any scientist, but specifically for your chosen field. If you had something like this in the frequency domain, I'm going to say this is going to be omega naught, and this is minus omega naught. Those are just arbitrary values. And then I had a function like this, where this is going to be omega naught plus b, and this point will be omega naught minus b. Same deal here. I'm going to have this point is going to be omega b, or I'm just calling b, pardon, b minus omega naught. This point is going to be minus omega naught minus b. And the height of this, I'll make it a half to make it easy on myself. Now, if you take a look at that, and this is your x of omega, and I want the time domain function to cause that. I want you to just think for a second. You see triangles, right? Do you know the time domain function to cause the triangle waveform? We just did it, didn't we? We can scale, right? But now we have something that's occurring that's interesting. It's a shifting, and it's a shifting of the same magnitude in both directions, and both are shifted positive in positive values. We don't have a in other words, this is not going to be an odd function. Follow me? All right, the minute you see a functional spectrum shifted to plus and minus omega naught centered there, right, you think cosine omega naught t. Got it? The minute you see that. Now, if this one was negative, like that, or this one was negative, then you think sine omega naught t, all right? Now, what is the transform pairing of property? I know that x of t times cosine of omega naught t automatically shifts out to 1/2 x of omega plus omega naught plus x of omega minus omega naught. Don't I, class? Right? Now look, this right here, x of omega plus omega naught, is based on the function x of omega, right? It's just shifted. So if you look at this, what is this function? Well, that sure looks like what? It looks like 1/2, right? I'll tell you what it looks like. This function right here is simply going to have a height of 1/2, triangle function. Its width is 2b, right? And it's centered at what? Omega plus omega naught. Correct, class? Do y'all see that? What about this function right here? That function is 1/2 times x of 2b, that's the width of omega minus omega naught. Correct, class? Are you with me? The x of omega that I'm really talking about, sorry, let me just put in the triangle. This is going to be 1/2 triangle of 2b here, right? And that's omega minus omega naught. Do you all agree with that? Because it's centered, the triangle function is centered where this is 0, so where omega equals omega naught is where it's centered, correct? Now take a look at that. That means what? Frankly, that entire, I mean, what can we do with this one? You all see that's a triangle waveform, simply multiply by cosine, right? So we can say really what we have here is a triangle waveform with a 1/2 magnitude here and here, which means it's split. It literally, the 1/2 right here can be put there and there, correct? And the only thing we need is what? We need the inverse of just the triangle function of width 2b. Do you agree with that? Do you agree? I had the width before is 2, correct? Now it's 2b, correct, class? So what we can say is this, and I don't want to confuse you on this. I'm going to go right to this point, and I know before I had, this was tau over 4 pi when I scaled it, I believe, right? And this is t times t tau over 4 before, correct?
Yes, sir.
And this was tau, correct, class, before? Isn't that right? I had to, there's a 2 pi there, and there was a 2 there, I had to get a 4 pi downstairs. Now, when you look at that for R's, right? R's has 2b here. I hope I'm being clear about this. That means this tau is 2b, and this tau would be 2b, which makes this coefficient just b over 2. And I can make this what? B over 2 pi. Correct, class? Isn't that right? Now, follow me. This function here is what's going to be multiplied by the cosine. So if I take that function, which is b over 2 pi times sinc squared of t times b over 2 times cosine of omega naught t, that would give me that functional form, which would be 1/2. Well, I gotta be careful about that. Yeah, it will. 1/2, and then it's going to be gamma of 2b, triangle of 2b, omega plus omega naught plus triangle of 2b, omega minus omega naught. Do you all agree with me, class?
Mm-hmm.
You have a suspicion, Josh. You're looking very suspiciously. Did you see what I did or not?
Yes,
Now this way is easy to see, right? But now look at the frequency domain and go backwards. Make sure your eyes catch that. Anytime you have the actual waveform split evenly in frequency domain, the transform the frequency like this, what it really looks is a base waveform that was here multiplied by a cosine. That's what you get. All right, so you automatically know that this triangle function is what is going to be related to the x of t. The splitting of plus and minus omega naught occurs because of the cosine omega naught t. Got it? How many see this right here? Please make sure you see that. What would be the difference if it was a sine? Suppose this was minus that, and it would be down like this. Well, then what? This would be a minus, right? All right? We're almost there. We don't have a j, do we? So we'd have to multiply both sides by a j here and here. Now, to tell you the truth, you don't get a j in the time domain. That's actually going to be a phase term that would be absorbed by the cosine, but I'll talk about that later. If you ever see something where it goes negative like that, think sine. Two positive things like that are symmetric and even function, you got a cosine. It's real important. All right, class? Fair enough. Did you have another question? Because I know. Yeah.
Just another random question. What would be the most likely convolution question you'd put on a
Most likely probabilistic. I mean, you want me to come up with a question that like has everything built into it? I could take a convolution of e to the minus at sine of omega naught t, u of t, and convolve it with something like a ramp function. Right? Now that's just about covers the whole 9 yards. Would it be a very difficult convolution if you didn't know properties and didn't know some tricks? Probably the things I'd recommend you focus on are exponential decays, u of t's, pulse functions, and simple ramp functions, things that go linearly up or linearly down, straight lines. I'm not going to give you something too extreme. I'm sympathetic to the fact that integration by parts is torture. So I'm not going to do that to you. Are you with me, class? I mean, we can go through a host of them, but the problem sets, if you've done them and you understand, I mean, you can basically extrapolate. Maybe instead of a triangle or something, I have something that goes up, levels off, goes down again. I want to convolve it with like a pulse, all right? Something like that. Those are really what? Classes of convolution or straight lines or simple exponential decays. But the homework I gave you is very representative. Look at all my old tests. Right? You don't see any real bizarre functions. I know somebody that would give you a bizarre one to teach you. He's not teaching in my class. It's not me.
If your height was like 1, would you just multiply the outside by 2?
That's right. 2, 2. That's it. That's a nice thing. These scale perfectly. It's not inverse scale. What else? I'm surprised you don't have at least 1 and 2. Figured you'd have some. I mean, questions about possible, you know.
I mean, I was just thinking like, I don't know, just about the implications of if you had a non-even.
Odd function?
Yeah, yeah,
Odd function here, split.
right.
You want to do a real quick one? Yeah. How about I give you one that's simple? You'll get this. Just make sure you know the property. It's a very simple function. Break it down to what does it look like, what does it transform to the base function, and then when it's multiplied, what will cause that multiplication. So let's do it this way. This is the omega domain. I'm going to come down to minus omega naught. Matter of fact, why don't I nail this down with a real number? I'm going to go to minus 3 plus 3. I'm going to have a function that looks like this. Minus 2, minus 1, height here of 1. And then I'm going to have the functional form. This is omega. 2, 4. That's going to go down like this. And minus 1 is the height there. This is my x of omega. Say again?
That's -4.
This is minus 4. Boy. Yeah, it's a function that's now got an odd symmetry. All right, now that one, the minute you see that, first thing you do, is just think of what would cause that back at the base frequency, or really when there's no frequency shift. I'm gonna do it right here. I wanna leave, no I don't. So what I'm gonna do is say, if I have this function in the frequency domain, what caused that in the time domain? This is a really good exercise. What's the h of t that caused that? Now, you all see that looks like a pulse. About as obvious as it gets, right? So some people know this off the top of their heads, but we'll use duality to get it if you don't. So first we know what? That a pulse function in time goes to tau, right, times the sinc of omega tau over 2. Agree? Work with me now. Use duality. Duality says what? I take the frequency domain function and I go ahead and say it's tau times the sinc of not omega but t tau over 2, right? What do I do over here? There's one thing that's the first thing you put down, class? 2 pi. So now I put down 2 pi, and I put p tau of, class, minus omega, right? Before I write minus omega, is the pulse function, is p tau of minus omega, is that an even function? Yes, so I can get rid of the minus, right? Even means it's the same, it's symmetric about the axis. So I'm just going to make it of omega. Okay? What's my next step from the audience? Don, I want to do something that, think of what you do to a fish before you eat it. Scaling, right? I'm going to scale this, not filleting, scaling. Filleting, you know, not the word we're looking for here. Agreed? What?
Would you not be able to make a positive omega since that's not an even function?
It is an even function. That's an
So
even.
you're not looking at
I am not there yet. This is the base function, right? We're working with, I want to see what caused this, all right? Got me? Remember, I know a property that'll give me that odd symmetry, right? Not the cosine multiplication, but the sine of omega naught t will get me that odd. I'll show you in a second. Anyway, are you with me now? Help me fill in the tau. What is tau?
2.
Everybody's suspicious. It's a trick. It's a trick. No, it's 2. It's 2. So get rid of that. So I've got sinc over pi. Agreed? All right, oh, sorry. The 2 here cancels this. So it's this. It's just the sinc of t. Agreed? Now, think to yourself, this is like x of t, right? This is like x of omega. Just think about it for a second. Agreed, everyone? Now, what do we know happens if I have x of t times the sine of omega naught t? I just did this, I did the cosine. That goes to what? J over 2, quantity x of omega plus omega naught minus x of omega minus omega naught. Agreed, class? Agreed?
Yes, sir.
Now, you'll notice I got a plus function of x, and I'm going to make this x, this pulse of width 2 of omega. Understand? Follow me? I'm just going to say my x of omega is that. Then I'm going to put a pulse of width 2 of omega plus omega naught. What is omega naught?
3.
It's 3. Agreed? Can you all see that? That's how far it was shifted in the frequency domain either way. It's where it's centered. So I'm going to go ahead and say this will be j over 2, and this is going to be that, the pulse function of width 2 of omega plus 3 minus the pulse fish function of width 2 of omega minus 3. Now, that's what would happen if it was my x of t here, right, times that sine of omega naught t. Correct, class? But what do we see? The scale factor on this and that is 1, right? So let me go back and I'll put the whole thing in and you'll see it. This is really going to be the sine, or the sinc of t over pi times the cosine, times the sine of 3t. Agreed? That's what would give us that exact. But there's two things that we have to do. We first have to bump that up by 2, or we have to multiply both by 2, right, to get it to a height of 1. You all see that? Because the height is 1, correct? I mean, can you see that that's 1? This is a half, right? So we have to multiply both sides by 2. And in doing that, this gets a 2 out in front. And then the next thing is what? Get rid of the j, or divide by j, or multiply by minus j. If you divide by j, it gets rid of that. Right? And that would be the right answer. Now I'm going to tell you one thing. The j and the time domain is troubling to everybody. I know that. But what you can do, and I'm not going to do, this is the right answer. Just trust me, it's the right answer. This can be absorbed into that sine. And I'm not going to do it right now, but anytime you see j, it's a 90-degree phase shift. If you got a sine omega t or cosine omega t, you can either add or subtract it in there. And I'll worry about that at another time. This is the right answer. Do you see that? You asked it, right? All right, does that answer your question?
Yeah, I was just wondering if you took something like that and then like multiplied it by another.
Well, then it would shift. What he's saying is if you take this function, and then I multiply that function, this function right here that caused that function, by, say, a cosine of 20t, right? Now we take this exact spectrum and it would shift it out, center that spectrum at 20, this whole thing would be centered about that point at plus and minus 20 omega, right? And the height of those would be crunched by half. Follow me on that? That's it. Yes?
So theoretically, if everything was shifted 1 over to the right, would the x of t just have the e to the negative?
No, you're looking at the time domain, right? When you get frequency shifts, it always is going to be the coefficient here. Sine of 3t. 3 is the frequency shift, right?
Right. But if it wasn't centered about 0, but was centered about 1?
Well, I think I know where you're going with this. Let's just do, suppose you had this. I think I know what you're doing. Suppose we didn't have a symmetric function at all, odd or even. Suppose we just had this, where this is going to be omega naught, and this is omega naught minus b, omega naught plus b, and the height of this is 1. Right? All right, what causes that? You nailed it with what you just said. What causes that? Let me just show you. All right? We know if we have any function x of t times e to the j omega naught t, that transforms as x of omega minus omega naught. Do you follow me on that? Agree? That just frequency shifts whatever you had as x omega out to omega naught, right? Now that's a pulse function. If you just look at x of t, if x of t is in the frequency domain, x of omega is simply what? It's a pulse of width 2b, right, of omega. That would be vx of omega, right? It's shifted. What causes that? We just did this. Well, that would be what? The sinc function of what? Sinc over pi, correct? Of what?
TB over
Well,
2.
it would be, well, the problem. It would actually be what? The tau there would be 2b, right? So it's really what? T times b in here. So this would be sinc of t times b here would render that, right? Correct, class? Hope I'm answering your question. You follow me? Now, if I take that function right here, and I multiply it by e to the j omega t, then it takes this pulse and it simply shifts it up there and there is no scaling. That's something that has no symmetry at all. Agreed? Now, other questions? Spent the whole thing, I was gonna do something else. Other questions about this? Now remember, op amps, that's basic circuits with the laws, right? No current into the terminals, no voltage between the terminals, and there's some simple transfer function relationships for operational amplifiers. I would think this way. One convolution problem for sure, at least one, but I'm going to just tell you, I won't put a discrete time convolution, it'll be continuous time convolution of some form that you've seen before. I'll ask you to show me directly, which one you're not going to flip, you draw it, then the flip and the shift, and then finally the answers, and you're going to give them for the different time domains, and I'll be a stickler for this. For t less than 0 to have a certain value, from t equals 0 to maybe 5, one value, from 5 to 10 another, and beyond 10 another. Follow me on this? You know how there's domains, right, where different answers appear. After convolution, for the Laplace transforms, you'll be expected to know how to get the Laplace transform of something and the inverse Laplace. And I would think probably in terms of circuits / op-amps kind of problems, because that's more applied to our area, not just general theory. But definitely Laplace transforms. Remember what negative feedback looks like with that too. Remember, I had things, if there are two series stages, you just multiply the transfer functions. Two parallel stages, you add the transfer functions times the incoming functions. And if you have negative feedback, you take what? The forward gain divided by 1 plus the forward gain times the reverse gain, the beta factor, right? You all know what I'm talking about with negative feedback, right? Make sure you know how to do that. For the Fourier series analysis, so think Laplace, convolution, Fourier series, getting the C of n values right, knowing how to get the average value. And if I ask to evaluate C of n for a given value of n, it's usually trivial if you get the right answer. So just remember, I don't give crazy complex stuff, because you don't have a calculator. But if you had if C of n was pi over n, for n greater than 1. If I ask for the value of C of n at n equals 1, it's pi. It's that kind of stuff that I would ask for. I won't ask you the thing to put into a single-sided cosine waveform with circuit analysis. That's mainly useful when you're doing computer programming for input-output relationships. Now with Fourier transforms, again, the power of duality is something I think about. Remember, any function that is non-zero values for t greater than 0, with the exception of u of t, if you have the Laplace transform, you have the Fourier by just replacing s by j omega, right? And the one that's a little troublesome, if you have u of t, well, I'll just put up the troublesome ones. Some of the troublesome. There's always going to be one I'm going to miss, naturally. But if you think about this, if I have 1, what does it go to if we're talking about Fourier transforms? That's right, 2 pi delta of omega, not something we get using the actual definition of Fourier transform, because it's an undefined. I use duality to get that, right? What happens if we have, another one is u of t. U of t goes to the 1 over s with s replaced by j omega, but there's that pi times delta of omega nasty right there also, because it has a value that's dc, you might say. We get that from duality. Then, after u of t, really, I'm not going to put them all down there. This can be a little problematic. I think that the rest of them are, the e to the minus at u of t here, that's pretty straightforward. That's just 1 over a plus j omega, right? That's a straightforward one. And the pulse, we just did the pulse in the triangle. And if they're multiplied by cosine or sine, what happens, right? Last one, suppose you ran into this. Suppose I had e to the minus at times cosine omega naught t times u of t, and I wanted to transform that. Well, you can get it several ways. Probably some of you memorized it, because you remember, you know what? You know the Laplace transform of that, don't you? How many know the Laplace transform? If you know the Laplace transform of that, you're golden. Just take j omega, or take s and replace it by j omega, and you got it for you. Now, if you don't know it, you could do this. You could say that's x of t, e to the minus at u of t. Well, that breaks down as what? 1 over j omega, or plus a, right? Then if it's multiplied by cosine omega t, you know you take that function, multiply it by 1/2, and you take 1 over what? J of omega plus omega naught plus a, plus 1 over j omega minus omega naught plus a, right? And you could get it that way too, using a property, right? Now, I just mentioned this, I'm not sure I'd go there, but if I multiply the whole thing by t, then you would take this one, right? And you would apply a property, wouldn't you? What property would you apply? If it was Fourier? It would be j times the derivative with respect to omega of the transform of that with respect to omega. Got it, class? That's the way you think about this. That's a little bothersome. Any other questions? We're getting away game, right? Are we favored or not? Does everybody know? It's Mississippi State, right?
Yeah.
It's probably close. We got 3 points of it, but I don't know. Is anybody going?